what are transducers exactly? Transducers basically can convert photons between different wavelengths. So, for instance, we might have a photon with a larger wavelength that goes through a transducer and becomes a photon with a smaller wavelength. In our metro area network example, we had these transducers situated next to the quantum memories in order to basically kind of act as an energy converter between the quantum memory and the photons that travel on the network. But why would we actually need these transducers? Like, wouldn't it be possible to just operate everything at the same energy and not have to convert between energies? Maybe we could pick a photon so that the photon's energy is exactly equal to the energy difference or in the atom or in the qubit. Well, it turns out that there is a reason that transducers are useful in many cases, although maybe not necessarily always required. And this reason has to do with the fact that low-loss fibers are at 1550 nanometers. So basically, we can look up the attenuations for fibers that operate for different wavelength qubits. And I've done that in this table on this slide. And you can see that at 1550 nanometers, the attenuation, or basically loss, is pretty low. It's 0.18 decibel per kilometer. But as we go to smaller and smaller wavelengths, this attenuation increases and increases. And this pattern isn't by accident. This is actually happening for fundamental physical reasons. Basically, at shorter wavelengths, Rayleigh scattering of the inhomogeneities in the fiber become really important, and you get more and more loss. And at also, kind of incidentally, at 1400 nanometers, there's actually pretty strong absorption from water. So it turns out that there are two windows for telecommunications that are really viable, and these windows are around 1500 nanometers and around 1300 nanometers. So if we want to be able to have quantum networks that go across really long distances, we would probably want to try to use photons and fibers operating at around 1500 or 1300 nanometers. However, it turns out that the stationary qubits that are used in quantum memories will emit and absorb photons mainly around 600 to 900 nanometer wavelengths. This is, of course, much smaller than these telecom photons. So, in this table I've included on this slide, this shows a couple of the different wavelengths associated with different quantum memories. So for nitrogen vacancy centers, which is a type of diamond defect, the wavelength is 637 nanometers. For silicon vacancy centers, the wavelength is 737 nanometers. For rubidium atoms, 795 nanometers. There actually are some quantum memories with photonic wavelengths that are actually in the telecom. So for instance, erbium, which is a rare earth ion, operates at 1536 nanometers. So this is definitely a promising area of research and definitely a promising candidate for quantum memories. There are some drawbacks of erbium quantum memories, which is currently some quantum operations are a bit trickier to perform with rare earth ion quantum memories. For instance, it's really useful to be able to have a local CNOT gate in order to do quantum entanglement purification protocols. And this is actually tricky to implement right now with erbium ions. However, this is still a very promising quantum memory with research ongoing. But because of this, it is useful to be able to have transducers which can do this conversion. and allow you to have stationary qubits that have one energy difference or one wavelength, and photonic qubits that will be at a different wavelength.